Hi everyone, welcome back to the channel. Today we're going to be looking at points of inflection. Okay, what is actually points of inflection? Points of inflection are points or a point that occurs when there is a change in concavity. Okay, let's see, what does that mean? So if as you see in the screen, there's like three curves there, yeah, and there's a change in concavity in the curve. So like okay, I'm gonna point out, yeah. So the first curve is like, this is the concavity is like concave down, so it's facing down, okay. And then there's a part that's gonna go concave up, so it's facing up. Now if you see that I've already put a dot, so there's a transition from concave down to concave up, and that point of transition is what we call point of inflection. Okay, so when there's a change in concavity, it can be from concave down to concave up, or concave up to concave down. The point of transition, we call it inflection point. Okay, there's inflection point. I'm going to put it there. There's also the last curve. Also, they also have inflection points. So this is a concave down and then concave up, even though it's not that obvious, the concavity, but it is still concave down and then going to concave up. So, right, again, this is the inflection point. Inflection, or points of inflection, or inflection point. Okay, so now we already know the inflection point. Now we're gonna put like symbols on the concave up, concave down, because it's important to know when is it concave down. So apart from looking at the curve, and obviously we can see when it's concave up or concave down, but we also need to know when is it, like not just by looking at the curve, but we need to know like what is it, it's going to be concave down. So a graph will have a concave down when the second derivative is negative. Okay, so when the second derivative is negative, then the graph is gonna be concave down. And then if the second derivative is positive, okay, there's gonna be concave up. Why it's like that, then we need to discuss it in another lesson, yeah, because it's going to take like a while. Okay, so when a graph is concave down, the second derivative is negative, and then when a graph is concave up, the second derivative is positive. So when there's a transition from second derivative negative and then second derivative positive, there's going to be a point of transition. Okay, so from negative to positive, usually, well, it's not usually, but always, you always have to go through zero. Okay, you always have to go through zero. So at the point of inflection or inflection point, the second derivative is going to be zero. Why? Because there's a transition from second derivative negative to second derivative positive. So you're going to go through zero. It's also going to occur when it's concave up. So the second graph, if you see the second curve, there's a second derivative positive, okay, because concave up, and then second derivative negative because it's concave down, and that there's a transition. So if you go from positive to negative, you're going to pass zero. So at the inflection point, you're going to have second derivative equals to zero. Okay, and we can apply that also for the third graph. So there's a second derivative equals to zero. Okay, so in conclusion, points of inflection is going to occur, okay, when the second derivative is zero and when there's a change in concavity. Okay, so first, second derivative is zero, and then there's a change in concavity. Okay, so again, I'm going to repeat. Points of inflection is going to occur first when the second derivative is zero, and then when there's a change in concavity. Okay, because it's not always, when the second derivative is zero, it's not always going to be a point of inflection, because there's going to be a certain case when the second derivative is zero, but then there's no change in concavity. Okay, so that's that. Okay, that's one. So okay, we already know how to find the points of inflection. Okay, now we're gonna figure out the type of inflection or the type of the inflection point. Now again, I want you to guys have a look at the graph. Okay, so there's a lot here. There's a lot that I'm introducing, yeah? So I'm gonna have a look. I want you guys to have a look at the graph. Let's check the first curve, the one on the left, yeah? So if you see, at the points of inflection, there is a slope. See the slope, okay? What color I'm still gonna be using red, yeah? We see at points of inflection, the slope is going down, okay? For the first graph, the left one, the slope is going down. See, I'm putting a red line, okay? When the slope is going down, okay, so when the slope is going down, then the first derivative is negative. Why it's like that? It's actually in the previous lesson when we were learning about gradient, okay? So when the slope is going down, then the first derivative, sorry, did I say second derivative before? The first derivative is going to be negative, okay? Now let's have a look at the second graph, okay? The one in the middle. Okay, so this one, if you see the point of inflection, there's also a slope, but it's going up, okay? It's going up. So when the slope is going up, then the first derivative is positive. Whoops, that's negative. It's positive. Okay. Now let's have a look at the third graph, the third curve, the one on the right, yeah? So if you see there, the inflection point is like if you make if you draw a line, it's just like horizontal, yeah? Just like a flat horizontal. So it means when it's like horizontal, then the first derivative is 0. So it's sloping down like the one on the first graph. The first derivative is negative. When it's sloping up, okay, when the inflection point is at a line, when it's sloping up, the first derivative is positive, so like the second graph. And then when the inflection point is at a line that's horizontal, then the first derivative is 0. Okay? Now, I'm still going to introduce you to another terminology. Okay, so when the inflection point is at a line that's going down or going up, then we call it non-stationary inflection. So this is a non-stationary inflection. Okay, so both the left and the one in the middle, they're both non-stationary inflection. Non-stationary inflection, okay? So when the first derivative is either negative or positive or negative, then it's non-stationary inflection. But when the first derivative is 0 or the inflection point is at a line when it's horizontal, it's called stationary inflection. Okay, so we have it, yeah? So I'm going to repeat. How do we find the point of inflection? Okay, so because that's the first point that we need to do is first, how do we find the point of inflection is when the second derivative equals to 0 and there's a change in concavity. So if you see, I'm drawing like there's a change in concavity. So we need to check 2, yeah? Second derivative equals to 0 and there's a change in concavity, okay? And what are the type of inflection point? There's 2. So there's a stationary and non-stationary. Okay. Stationary is when the first derivative equals to 0. Non-stationary, oopsie, I'm doing a second one. Non-stationary is when the first derivative is either positive or negative. Okay, so we've learned all of the important points and the important terminologies. Now we're going to do it. Yeah, we're going to find the points of inflection of fx. Okay, let's write down. Fx equals 3x to the power 4 plus 4x cubed minus 1. Okay, let's start, yeah? So to find the points of inflection or the inflection point, like what I said before, we need to have the second derivative equals to 0. So let's find the first derivative first. Okay, so the first derivative is 12x to the power of 3 plus 12x to the power of 2. and then the minus 1 is gone, okay? Because the minus 1 is a constant, so it's going to be 0, yeah? Okay, and then we're going to go to the second derivative. We need both, yeah, the first and the second derivative. Okay, the second derivative is going to be, so 12 times 3, which is 36, 36x to the power of 2, and then plus 24x. So we have both the first derivative and the second derivative. And because we're looking for the point of inflection, the first thing that we need to do is second derivative equals to 0. Okay, so second derivative equals to 0, okay, which is 36x squared plus 24x equals to 0. Okay, we're going to factorize that, yeah? We're going to ditch out the common. So the common, there's 12x, yeah? So I'm ditching the highest possible common, yeah? So common factor, so it's 12x. Okay, yeah, I think so. Oh no, oh yeah, that's right, it's 12x. And then the one left inside the bracket is 3x plus 2 equals to 0. Okay, so now it means it's 12x equals to 0, or 3x plus 2 equals to 0. X equals 0, or x equals negative 2 over 3. Okay, so we have it. Because it's points, so we need to find the y. So it's x here. We have two x's, so x equals 0, and then okay, it's neat. So x equals 0, and the other one is negative 2 over 3. Because it's points, so we need to find the y, yeah? So it's coordinate, yeah? So how do we find the y? We input the 0 and the negative 2 over 3 to, okay, pay attention to this. Can you see the pink arrow? To the real function. Yeah, to the real function. And I think for the x equals 0, it's easy, yeah? So you input in the fx in the real function, and we get 0, and then the y is going to be negative 1, okay? And then, but then for the negative 2 over 3, we might need to use a calculator. I actually already checked. I hope I didn't miscalculate, but the y is going to be negative 43 over 27. Okay, so negative 2 over 3, comma, negative 43 over 27, and then 0, comma, negative 1. Are those 2 points, are we sure that they are points of inflection? No. We don't know yet if it's really point of inflection, because it only fulfills the first one, which is the second derivative equals to 0. We need to check whether on the left side, on the right side of those points, there is a change in concavity. If there isn't, then they're not the points of inflection, okay? Okay, so we're gonna check, yeah. Now, we know that negative 2 over 3 is approximately negative 0.67. Why do we need that? Why do we need to know that? Because it's just for us to know what to choose for the neighbors of negative 2 over 3. What's on the left and not on the right side. Okay, let's check whether there's a change in concavity. I'm going to use the table method. Do you need to use this method? No, there's like, you can use number line, yeah? But I like using this one better, okay? So this is the x, okay? We're going to check the second derivative. You'll see why. Just follow what I'm doing, yeah? Then the... oh, okay, I'm gonna put shape first. This is shape here. Okay, and then the first derivative. And then maybe the shape also. There's no harm. Okay, so I'm gonna like do this. I'll have the smaller one, which is negative 2 over 3 here. Then 0 here. Okay, so we're gonna test the neighbors of negative 2 over 3 and 0. Okay, so we're gonna test the numbers that is on the left side, okay, of negative 2 over 3. I'm gonna choose, because negative 2 over 3 is negative 0.7, so I'm gonna choose negative 1. So I'm just put here so people know what number I'm choosing is negative 1. And then I'm going to choose the number on the in between, yeah, in between negative 2 over 3 and 0. So I'm gonna put like negative 2 over 3 plus, means on the right side of negative 2 over 3. I'm gonna choose negative half. Okay, negative half. Okay. And then for the number that is on the right side of 0 or bigger than 0. So I'm going to put 0 plus. I'm going to choose 1. Okay. So what are we going to do with those numbers? We're going to input in the second derivative. Okay. So can you see I'm shading the second derivative part because we want to know the concavity. Remember, when the second derivative is negative, is concave down. When the second derivative is positive, is concave up. But let's fill in the point that we got first. So at -2/3, the second derivative 0. Oh, why did I use that? Sorry. The second derivative is 0. And then at x equals 0, the second derivative is also 0 because that's how we got it. Okay, let's input -1. This one here, the one that we chose. That. Oh, sorry, I kept on using the wrong one. Okay, so this one here, the one that we chose for the left side of -2/3, we're going to put it in the second derivative. Okay, we're going to put it here. People, can you see the arrow? Yeah, we're going to put in the second derivative. And I'm going to use my calculator, and I have the answer already. So if I put -1 in the second derivative, I will get 12. I hope I didn't miscalculate it, but I will get 12. So 12, just 12 is a positive number. So I'm going to put positive there. And then if I input -½ on the second derivative, okay, the second derivative, I will get, when I put in the calculator, you can put also in the calculator, I will get -3. Okay, so -3 is a negative number. And then if I input 1, okay, on the right side of 0, I will get 60. Yeah, I think I guess, yeah, I'll get 60. And 60 is a positive number. Okay, so guys, let's do the shape. Now, the shape of a curve when the second derivative is positive is concave up. And then the shape when the second derivative is negative is concave down. And the shape when the second derivative is positive is concave up. So then we can conclude that this here, the point that we got before, it's a point where there's a transition from concave up to concave down to concave up. So yes, -2/3, -43/27 and 0, -1, they are points of inflection or inflection points. So yes, they are inflection point. So this is inflection. This is also inflection. Okay, so they're both inflection point. So we know that. But then remember, we need to also determine what type of inflection. Remember, there's two, yeah? There's a stationary and non-stationary. So we need to test those 2 points because we already tested that they are inflection. Now we need to figure out whether they are stationary or non-stationary. Okay, so the box that we need to fill is this box here because we are testing the point itself, yeah? So I'm going to input the -2/3 on the first derivative, okay? I'm going to put the arrow, first derivative, so people have a look. I'm putting arrow on the first. Can you see the arrow there? I'm making the arrow on the first derivative. So I'm putting -2/3, okay, in the first derivative. Okay, let's have a look. I'm going to use my calculator now. So hopefully it's not going to take too much time. So 12, okay, times, and then in bracket, okay, 2/3. Okay, sorry if it takes a little while. Okay, -2/3. Okay, I'm inputting in the first derivative, yeah, and then cube. Okay, cube. Oh, sorry, I'm like pretty slow. Then 12 times in bracket -2/3. Okay, and then I square it, and I will have a positive number is 16/9. Okay, so I'll put it in. So this is a positive. Can I put 0? Okay, for the 0, if I input in the first derivative, it's also 0. So people, how's the shape? So the shape, if the first derivative is positive, is going up, and then if the first derivative is 0, it's like just like horizontal. So now we know that 0, -1 is a non-stationary inflection. Oh, sorry, I got it the other way around. The 0, 1 is stationary inflection. So this is stationary. because the first derivative at 0 comma negative 1 is 0, and then the negative 2 over 3 comma negative 43 over 27, it's non-stationary because the first derivative is positive. Non-stationary. Okay, there we go. We got it? Okay, so to conclude, how do we find the point of inflection? Okay, to find the point of inflection, the first thing that we need to do is we need to find the point where the second derivative is 0. Okay, after we get the point, we test whether those 2 points or a point or maybe 3 points that we got is actually a transition, is the transition of the concavity or not. Yeah, so that's the second thing that we need to do to find the point of inflection. If those points that you got is actually the transition in concavity, then they are the points of inflection. Okay, after we're like, oh yeah, they're the points of inflection, then you need to determine the type of inflection point, because there's two, stationary and non-stationary. Okay, then you test those 2 points using the first derivative. If the result of the first derivative, when you input those points in, is positive or negative, then we call it non-stationary. Okay, if the result of the first derivative is 0, then we call it stationary inflection. Okay, I hope this is helpful. Yeah, I will see everyone in the next lesson. Okay, bye bye.